In the last lecture we had looked at various types of discriminant functions, the rules that one can derive when we have a multi-population problem. So specifically we had discussed the problem like this, that if we have got C populations pi 1, pi 2, pi c, and then under a general classification problem, if we consider costs of misclassification, prior probabilities and so on, then what sort of optimum rules are desirable. Say for example, we had derived the rule which would minimize the expected cost of misclassification, appropriately derived under such a C population setup, and we had also looked at the rule which would minimize actually the total probability of misclassification. The two rules were seen to be the same when we have got the following formulation, that we were looking at a rule that would minimize the expected cost of misclassification, that was given by this particular expression. And then we had seen that under a small note, that under the equal cost setup, if we assume that the costs of misclassification quantities are all assumed to be equal, then naturally one is going to get the rule which is going to be the total probability of misclassification minimizing rule, and that is what we had seen in the last lecture. So in this lecture, what first we are going to look at is an example of the type of theory that we had developed in the last lecture, and then we will also talk about other popular type of classification functions. Let us first then look at this example. We have got the following example. This is the cost prior table corresponding to the 3 population setup. So we have got 3 populations which are, say, denoted by pi 1, pi 2 and pi 3. Let us make this particular table which is going to give us the cost of misclassification and also the prior probabilities of the corresponding populations. So suppose we have on this side true membership of that individual. Now an individual can either belong to pi 1, or it can belong to pi 2, or it can belong to pi 3, because these 3 are the 3 possible populations. And corresponding to the true membership, corresponding to our classification rule, we can get that object being classified as coming from either pi 1. This is going to be the classification that is based on the classification rule in place. So it can be either of these 3, pi 1, pi 2 and pi 3. Right. Now if we have got an observation classified into pi 1, and if the true membership is really pi 1, then there should not be any cost of misclassification. So this entry here, which is C1 1, that is, it is coming from pi 1, it is getting classified into pi 1 itself. So that should be equal to 0. So all these 3 diagonal entries, C22 and C33, all these 3 quantities are zeros. The off diagonal elements are costs of misclassification. Suppose we have, for this hypothetical example, that this is equal to 100, this is equal to this is 500, this is equal to 100, this is equal to 50, this is equal to 10, this is equal to 50, and this is equal to 200. So this is the cost of misclassification table. Note that this cost of misclassification table, this matrix, actually 3 by 3 matrix, need not be a symmetric matrix, because we do not have the same costs. Like this one is C21 and the other one here on this matrix is C1 given 2, and it is not really natural to assume that the 2 will be equal, and hence we have 2 different misclassification costs corresponding to 2 such situations. Now let us have these prior probabilities also. So the prior probabilities of pi 1, pi 2 and pi 3 are given by, say, P1, which is in our notation P pi 1. So that is equal to, say, 0.05, this is equal to 0.60, say, and this is equal to 0.35. So these 3 are the 3 prior probabilities. The sum of these 3 of course is going to be equal to 1, because we are assuming that there are only 3 populations. This C here is equal to 3 anyway. In general we had denoted that by pi 1, pi 2, pi c, and this we have as 3, C equal to 3. Now suppose x naught under such a situation, cost prior table, x naught is a new observation, is say such that we have got the density at x naught corresponding to the respective populations pi 1, pi 2 and pi 3 are say given by f1 x naught. X naught is a multivariate observation. Say this is given by 0.01. This is f2 x naught. So that's the density of this variable of this multivariate vector x naught under the second population pi 2, that is equal to say given by 0.85, and this is f3 x naught. This is for the third population. This is say given by the difference, or it can be anything else also. This is going to be given by say 2. Now, corresponding to such a setup, we will implement what the type of optimum rule, optimum classification rules that we have learnt. So, we have got the cost structures to be not equal. So, we have the cost of misclassification to be taken into account, and hence we are going to compute the following quantities in order to implement the expected cost of. I will first say that what we are going to do, derive the classification, with respect to the observation, which is x naught. So, in order to do that, we are trying to find out the classification rule. So, this classification rule is one that is going to minimize the expected cost of misclassification. Classification rule minimizing the expected cost of misclassification. So, we need to compute the following quantities one after the other. This is going to be given by I equal to 1 to up to 3. There are 3 possible populations for I not equal to k. So, for specific choices of k, we are going to compute the quantity which is going to be given by this multiplied by Ck given I, right. Now, why do we need to compute this? We will have to find out for which k such an expression from among possible choices of k, which is 1, 2 and 3. This quantity is what we are going to get the smallest. Why is that so? Because in the general classification rule, when we were looking at expected cost of misclassification minimization rule, we had Rk to be that partition of the sample space. Rk is the region of all x's such that this quantity here needs to be the smallest, and hence we had got this classification rule that x to be allotted or allocated to pi k, for which we have this quantity for I not equal to k is smallest. So, in order to implement this expected cost of misclassification minimizing rule, what we need to do is to compute this quantity here for different choices of k equal to 1 to up to this quantity c, and then find out which is giving us the minimum, and that is going to give us the allocation corresponding to the rule which is minimizing the expected cost of misclassification, right. So, we compute this quantity for k equal to 1, k equal to 2 and k equal to 3. It is trivial to find out this term here for k equal to 1, 2 and 3. So, this is going to be I not equal to k, and hence if k is equal to 1, then I would start from 2, and then we will look at this particular product here, which is Ck given I. So, this can be computed very easily. This is P2 F2 x naught. Now, this k is equal to 1 in our case, because we are choosing k equal to 1. So, this is going to be 1 given to this plus the term corresponding to I equal to 3. So, that is P3 into F3 x naught, that into C1 given 3. So, using this cost prior table, one can compute what this quantity is equal to. It turns out that this is equal to 325. Now, similarly, this is the value of this quantity here for k equal to 1. Similarly, we need to find out what is this for k equal to 2. So, for k equal to 2, we will have an expression which is summation I equal to 1 to up to 3, and then this I is not equal to k, that is I is not equal to 2. So, the two terms in this summation would correspond to I equal to 1 and I equal to 3 of this expression, which is Pi Fi x naught into C k here is equal to 2. So, we can write it straight away as 2 given I. So, one can similarly compute it from the previous cost prior table, and this turns out to be that it has the value that it is 0.35.06, and for k equal to 3, this expression now summation for k not equal to I not equal to k. So, k being 3, this summation is from I equal to 1 to up to 2 terms. So, this Fi x naught into C k given I, this term here from the given data turns out that it is 102.03. So, we have computed this quantity here for every value of k. For k equal to 1, this turns out to be this, for k equal to 2, it turns out to be this, and for k equal to 3, this turns out to be this. So, if we have got a multi-population setup, say for k greater than 3, the same logic can actually be applied. So, one can look at all the values of k equal to 1 to up to c, and then look at the one which is giving us the minimum. In the present situation here, what we have is for k equal to 2, the expression which minimizes the expected cost of misclassification rule, that is giving us for k equal to 2 the minimum possible, that is 35.06 is minimum among these three observations, and hence what we have is that x naught for which we have got this density at x naught to be given by these values, that x naught is going to be allocated to the second population, and that is how this rule works. So, this implies that since we have got this summation I equal to 1 to up to 3 here, I not equal to k of the quantities Pi Fi x naught into C k I, this is smallest for k equal to 2, this we will have x naught being classified k equal to 2, x naught the new observation is to be allocated to the second population, that is pi 2. So, this is how this type of ECM minimizing rule works. Now, if we take a special case, in the previous example, suppose we take the costs of misclassification to be same. If costs of misclassification are assumed to be equal, then we need to just consider only the quantities which are F1 x naught, F2 x naught, F3 x naught, and the corresponding prior probabilities, that is P1, P2 and P3. Because if in this particular setup we now assume for simplicity that all these quantities are equal except those which are on the diagonal, then the special cost structure does not make any difference, and we will have this special case out here, what we said in the note, that under the equal cost setup, the ECM minimizing rule is what is going to lead us to the total probability of misclassification minimizing rule, and then we will allocate x to pi k if this quantity is smallest, wherein the cost structure of course comes out because they are the same, and then we are basically going to allocate x to pi k, the kth population, if this pk fkx is greater than pj fjx for j equal to 1 to up to c j not equal to k, and hence we would just be looking at, under such a situation, these 6 quantities. Now, what we have is the following quantity, that this is for the given data, what we have are the following quantities, that this P1 F1 x naught, that is equal to 0.0005 P2 F2 x naught for the given x naught to be equal to 0.510 and P3 F3 x naught, that is equal to 0.7. So, we have these three quantities to be given by this. Now, we are going to allocate x naught to that pi for which we have got one of these quantities to be the highest. And what is that? This one is the largest, since we have got in the present situation this P3 F3 x naught is greater than Pi Fi x naught for I equal to 1 and 2, that is leaving aside that k equal to 3 term on the right hand side. X naught is allotted to the third population, which is pi 3. So, this is in line with what the theory had suggested us, that we are going to allocate an observation x to pi k if this quantity on the left hand side is greater than all the c minus 1 quantities on the right hand side, and that is what was happening out here, that this is the highest among all the three, and hence this x naught, the new observation, is allotted to that third population, which is pi 3. Now, depending on the problem, the type of implementation of the theory can be simple, it can be difficult also. Now, let us look at some specific examples when we have classification problem for multivariate normal populations, classification with multivariate normal populations, multivariate normal populations. So, this is what we are going to look at. So, suppose we still have C populations, they are denoted by, as before, pi 1, pi 2, pi c. So, these are the C populations. Assume for simplicity that the cost structures are same, assume for simplicity, otherwise it is going to be a bit more complicated, nothing is going to change much. Assume for simplicity that this C k I are all same for k equal to 1 to up to c and k not equal to I, right. Now, if we look at the rule which minimizes the expected cost of misclassification, or the one which is going to minimize the total probability of misclassification, the two are going to be the same, because we have assumed for simplicity that the cost structures are same. Rule is allocate x to pi k if we have got this p k f k x to be equal to maximum over I of the quantities of the form which is pi fi x, right. That is, if we have got log of this quantity, log of pk fkx. Now, we know what is fkx because the kth population is a multivariate normal distribution. So, that let us at this point of time take this pi I to be a multivariate normal population, say m dimension, with a mean vector equal to mu I and a covariance matrix equal to sigma I, wherein we assume that this sigma I for every value of I is positive definite matrix. So, we will have to look at what this quantity is equal to. That is simple because we have got the multivariate normality. So, this would be log of pk, then we will have minus m by 2 log of 2 pi term, then we will have minus half log of determinant of pi k, and then the negative of the exponent, or rather the log of the exponent, minus half x minus mu k transpose sigma k inverse x minus mu k. So, that is our this log of pk times fk. This is equal to maximum over I of the respective quantities pi fi x quantities. Now let us define the quadratic discriminant function as following. Define a quadratic discriminant function or quadratic discriminant score, say. Let us denote that by its quadratic discriminant score for the ith population as the quantity, say delta I QDS quadratic discriminant score. This is for this point x to be equal to the quantity which actually matters, which is minus half log of determinant of sigma I minus half x minus mu I transpose sigma I inverse x minus mu I. This is what it comes there, and this in plus log of pi. Why do we take this and define it as a quadratic discriminant score? Because if we look at this log of pk fkx, this quantity is a constant which does not depend on pk, sigma k or mu k, which are the characteristics of the kth population, and hence what is going to matter when we are going to look at the maximum of this pi fi x's is the quantity which is comprising of this term and this particular term. So taking all those terms, the quadratic discriminant score for the ith population is defined in this way. So we have got I equal to 1 to up to c, and then rule is basically to allocate x to pi k if in terms of the quadratic discriminant scores this delta k of x quadratic discriminant score is the maximum over I of this delta I q ds terms. So the classification rule is going to be just based on these quadratic discriminant scores, right. Now in this particular setup, in the multi-population setup as what we have in here, if we take that the costs CKI's are not the same, then we will have to go back to the expected cost of misclassification minimizing rule, the general rule that we had derived, which was given by this following term. Then Rk would be the region for all x's, such that this we will have the term here to be minimum. In such a situation, the CKI's, which if they are not assumed to be the same or they cannot be taken to be the same, we will have to look at this particular expression and find out for which value of k left out in this summation here the quantity is going to be the smallest. But we have chosen it to be for simplicity that this cost structures are same, and hence the entire classification is going to be based on this quadratic discriminant score. Now it may be noted that when we are talking about this quadratic discriminant score and we are saying that the rule is to allocate x to pi k if we have got the quadratic discriminant score corresponding to the kth population is the maximum among all such quadratic discriminant scores. A few quantities here are unknown actually. There is mu I terms, sigma I terms, sigma I, sigma inverse or sigma I matrix in general actually is not known to us. So how do we implement for a given data? Given a learning sample, remember that we had talked about the learning sample. Learning sample is a sample for which we have got actually the cases being pre-classified. So it is basically the training sample wherein we have the feature vectors and the corresponding or rather the population marks, the population identification marks of the respective feature vectors. So these are containing actually the learning sample contains the pre-classified examples on which we are going to build our classification function. So given a learning sample L, we estimate mu I and sigma I and estimate the QDS for the ith population pi I as the corresponding say delta I QDS cap So that's the estimated quadratic discriminant score, and that's going to be given by minus half log determinant of SI hat, or just SI. SI is basically the estimate of sigma I matrix. So this minus half x minus x bar I transpose SI inverse x minus this x bar I, wherein this is the estimated sample mean based on the observations coming from pi I, because if we have got L, this is our learning sample. So this is our learning sample. Suppose in this learning sample we have got N1 observations from pi 1 population, N2 observations from pi 2 population, and similarly NC observations from the pi C population. Then based on these N1 observations, which are pre-classified, which have a tag, identification tag corresponding to the first population pi 1. So based on these N1 observation, one is going to compute, because these N1 observations are all multivariate observations. So one is going to compute this x bar I, which is the mean vector, which is the estimate rather of the mean vector of the first population, and SI, that 1 upon Ni minus 1 xi minus x bar into xi minus x bar transpose. So this is the estimate of sigma I matrix, and similarly for each of these sets of populations from the respective populations we can actually find out. So this would be x1 bar. So this is going to be x1 bar, and this is going to be our S1. This we have x2 bar. This is the mean vector computed from the N2 observations, and similarly for the Cth population based on NC observations, we have the mean vector being computed at x bar C, and SC is the corresponding estimate of the variance covariance matrix sigma C corresponding to the pi C population. So this is what is now in an implementable form. So one looks at the estimated quadratic discriminant scores of the respective populations, and the one which is going to give us the maximum, we will have the new observation to be allocated to that corresponding to that maximum of the estimated quadratic discriminant scores. Right. Now if we take a special case of the previous multivariate normal populations, if we have the special case that these pi I populations are multivariate normal m dimensional with mean vector as mu I, and the same covariance matrix for all the populations I equal to 1 to up to C, wherein the common sigma matrix is a positive definite matrix. So we have got the C populations pi 1, pi 2, pi C, all multivariate normal, with the mean vector being different for the different populations, the covariance matrix sigma remaining the same for all of these populations. Then the discriminant score, as in the previous example, the discriminant score for this setup is given by following exactly the same type of approach that we can look at pk fkx. Now these fkx's for the k populations will only differ by the corresponding mean vector quantity, and hence the discriminant score is going to be given by minus half, this is log of determinant of sigma, because the sigma matrix was assumed to be the same, and then if we split up that quadratic term there, then we will see that there is a term x transpose sigma inverse x, which does not vary from population to population, because sigma matrix is same for us, and hence this entire quantity here is going to be same for all the populations. So we will have this quantity to be same for all the populations. The terms that are going to be different is mu I transpose sigma inverse x. There will be a term which is twice here, because we will have this product here. Once we open up this term here, we will have an x transpose sigma inverse x, that is what the first term which is independent of k, that is what we had written, and then we will have this as x transpose mu k transpose sigma inverse x, and there will be a same term with an with a transpose coming out from x transpose sigma inverse mu k. However, there is a factor 2 in the denominator. So, eventually this 2 is going to be cancelled out, because we have a factor minus half sitting outside this minus the term which is dependent on mu I vector. So, it is mu I transpose sigma inverse mu I, and this plus this log of pi. So, what we have cleverly done is to look at the simplified version of this quadratic discriminant score, because the sigma matrix is same for all the populations, and hence this is going to be in the present situation going to be the same for all the populations, and the term x transpose sigma I inverse, sigma I is sigma here, and hence that term is going to be independent for the various choices of the population I. So, the terms that are going to vary now is this term here, and basically this term here. So, what we observe is that now the discriminant score can be written as a linear discriminant score, because the quadratic term here is independent of the ith population, and hence in this situation what one does is to define the linear discriminant score as, say, delta I linear discriminant score with respect to this observation x, which is now going to be given by this mu I transpose sigma inverse x minus half mu I transpose sigma inverse mu I, this plus log of pi, right. So, if this is the linear discriminant score corresponding to the ith population, we will allocate an observation x to pi k if the linear discriminant score corresponding to that kth population is going to give us the maximum. And hence, we have the following discriminant classification rule. Rule is to allocate x to pi k if we have delta k linear score with respect to x to be the maximum overall I of this delta I linear discriminant score with respect to all these x's, right. So, this is what is the rule, which is basically a linear discriminant score based rule. Now, once again we will have to look at this particular term here and then look at the sample counterpart of it, sample counterpart in the sense that when we have got the learning sample, then based on the learning sample we will have to compute each of these quantities. Now, note that mu I vectors, that is specific to the ith population, and hence that is going to be computed from the ni observations which belong to the pi I population. However, this sigma matrix we have assumed to be the same for each of the populations, and hence this sigma matrix is going to be computed as the pooled sample variance covariance matrix based on n1, n2, nc observations. Now, once again, given the learning sample, given this learning sample or learning set, learning sample script L, say the estimated linear discriminant score, the estimated linear discriminant score is going to be given by, say, delta I hat LDS at x, that is going to be given by the corresponding sample quantities x I bar transpose S inverse. I am going to define what these terms are, x this minus half x bar I S inverse x bar I this plus log of pi, where this x I bar is the sample mean of Ni observations pre-classified as from the pi I population, and this S matrix is going to be given by the following: summation Ni minus C I equal to 1 to up to C times this S matrix is going to be given by the pooled Ni minus 1 times Si I equal to 1 to up to C. So, this is basically the type of pooled sample variance covariance matrix. When we have two population, we say that N1 plus N2 minus 2 times S, the S being the pooled sample variance covariance matrix, that is equal to N1 minus 1 times S1 plus N2 minus 1 times S2, and hence this is what is the generalization of that. So, we have got this S matrix to be the pooled sample variance covariance matrix. Now, what are these SI quantities? These SI quantities are the sample variance covariance matrix, computed from the Ni observations from pi I population, right. So, those are basically the sample variance covariance matrices from each of these pre-classified Ni observations from the pi I population. So, based on this sample variance covariance matrix, what we can say is that we have the rule as to allocate x to pi k if we have got this delta k cap linear discriminant score corresponding to this x to be equal to the maximum over all I of all such estimated linear discriminant scores at this point x here. And I will just put it as a note that this linear discriminant score can be expressed as a distance, square distance actually. This above rule is equivalent to, because of the simple and obvious reasons, is equivalent to, I'll say that allocate x to pi k if we have got this minus half x minus x k bar, say transpose S inverse x minus x k bar, this plus log of p k is largest. This is so because what extra terms we have added here is an x transpose S inverse x that is going to remain the same for each and every population k, and hence just by adding that particular term we are able to express it in terms of this is basically the distance square di square x, that is assign this x to pi k the closest population, this of course closest population penalized by this particular term here, penalized by log of pk term, right. So, it is equivalent actually because the term that we have added out here is basically not going to vary from population to population. So, this is say dk square, and hence we have got this to be having the interpretation that we are going to assign x to pi k if that is that x is closest to the pi k population. So, this is about the type of classification rules that we are going to get if we have the possible C populations to be multivariate normal, either differing only by the mean vector or differing both by the mean vector and the variance covariance matrix. Now, let us now look at some other popular type of classification rules, the discriminant functions based on say 0-1 type of regression models, classification models which are going to be based on nearest neighbor classifiers, then logistic discriminant functions. So, let us start looking at those special cases. The first one that we are going to look at is classification model using a 0-1 response regression model. This is a very simple and intuitive way of looking at the classification problem. Suppose we represent the regression model as the following. In the standard multiple regression model, that it is x beta plus epsilon. Now we have got here, suppose this is n by 1, and hence this epsilon also is 1 by 1 n by 1, and we have got epsilon t. This is a sequence of say IID with mean 0 and some variance equal to sigma square term. Then we all know that the residual sum of squares with respect to this unknown vector, regression vector beta, is given by y minus x beta transpose y minus x beta, and then beta hat, which is the argument minimum with respect to beta of this residual sum of squares. So beta hat is one that minimizes this y minus x beta transpose y minus x beta, is going to be given by x transpose x inverse x transpose y. So we have got this beta hat to be equal to this. Now corresponding to this beta hat, the fitted value for the ith input vector is say given by y I hat, which is equal to say y hat of this x I vector, that is the ith input vector. It may have a constant 1 in the first entry if this model has got a constant term, and it will not be having that if we do not have a constant term there. So this is going to be given by x I transpose times this beta hat. So this is what we have at the ith input vector. For a new observation, x naught, the predicted value is going to be x naught transpose times this beta hat. Now based on this value of x naught transpose beta hat, we are going to give a classification rule. Suppose we have got a two class problem. Suppose we have a two class problem. That is, there are two possible populations, pi 1 and pi 2, and let us consider that the response variable is a class variable, say denoted by g, taking values either 0 or 1, 0 or 1. The fitted value y hats are converted to fitted classes in the following way. Class variable, say g hat, according to the rule, say I put g hat to be equal to 1 or 0. This is going to be 0 if we have the predicted y hat to be say less than or equal to 0.5. Now this is nothing special about 0.5, one can vary that also. So this is equal to 1 if we have got y hat to be greater than 0.5. So such a type of rule, which is going to be based on the predicted value y hat, and then from that continuous scale y hat what we have observed, if we look at using that y hat to frame this g hat, the fitted class variable, to take the value 0 if y hat is less than or equal to 0.5 and is equal to 1 if y hat is greater than this, then based on this regression model and a new given observation x naught, a value of this being at a predicted value y hat, say, we will be able to then give the class membership 0 or 1 based on the predicted value of y hat. This is a simple rule. This has got a decision boundary given by the following. So, the decision boundary is basically the set of x's such that we have got x prime beta hat that equal to 0.5. One can vary this particular constant here in order to get other type of decision boundaries. It is a simple rule. It is a simple rule. What one assumes is that the response variable is a 0 1, then apply a simple multiple regression type of setup and then get to the predicted class membership through the mapping as what we have given in here. Now, this simple concept here, what we have for this 0 1 response variable, can be generalized for a k class problem. Let us see that particular generalization to the k class problem. Suppose we have got a k class problem, meaning thereby we have got k populations pi 1, pi 2, pi k. These are the k possible populations, and then suppose under such a setup we are going to have the following. Suppose for the k classes we define k indicator variables in the following way, that we have got a yk, the kth indicator variable taking the value 1 and 0, 1 if response class is k and is equal to 0 if it is otherwise, right. So, we will have the corresponding k indicator variables y1, y2, yk. These are the k indicator variables which are going to give us the class memberships. Now, if we have the training sample consisting of n data points, if the training sample has n data points, then what we are going to have, then we will have corresponding to these k defined indicator variables a matrix y which is going to be an n by k matrix. So, this is the indicator response matrix. Now, each row here, each row has a single one entry and all other entries are zeros. Why is that so? Because if we have defined this yk, kth indicator variable, to take the value equal to 1 if the response is in class k and 0 if otherwise, and then let us look at this y, this is this y matrix, this is an n by k matrix. So, how is that going to look like? Now, these are corresponding to, this is the first observation in the training sample and this is the nth observation in the training sample, right. Now, we have here corresponding to the first observation the k indicator variables. Now, suppose that the first observation is belonging to say ith, suppose this is belonging to pi I, then the yi corresponding to that, this, if this is the ith position, then the yi corresponding to that would be equal to 1 and all others will be equal to 0. Similarly, for the second observation here, if that is belonging to some pi I prime, then at the I prime position, this vector, this row vector will contain the 1 entry and all other positions will have 0 entries. So, each of these rows of this matrix that we are going to have, which are going to be based on those y1, y2, yk, the k indicator variables. So, for the jth observation in general, we will have the corresponding entry in the column of y1, y2, yk, this particular row to be equal to 1 if the jth observation is belonging to that particular population in the training sample. And hence, this is how we are going to get this n cross k matrix of zeros and ones, wherein we will have a single entry 1 in each of these rows here, right. So, the entire data using the indicator, the k indicator variables y1, y2, yk, we are able to write it in terms of this n cross k matrix, which is the indicator response matrix. Each row of this particular matrix y has a single 1 entry and all other entries are 0. That is because of this simple reason out here. Now, what we are going to write is the following: define this model through this matrix y n cross k, which is going to be given by an X matrix, which is now having say p plus 1 columns, n rows corresponding to the n observations of this data. So, this we have n cross p plus 1, we have taken say a constant term here. So, that the first column of this X matrix would be constant and hence p plus 1, and we assume that there are p more explanatory variables, explanatory in the sense of giving us some clues about, or rather explanatory for the corresponding response variable, and this B is a matrix of unknown constants which is of dimension p plus 1 rows and k columns, and then corresponding to this Y matrix here we will have an E matrix here, which is the matrix of noise random variables, which is n by k, right. Now, if this is the noise part, if this is the explanatory part, and if this is the response matrix part, this is in the matrix regression setup, where B matrix p plus 1 by k is the matrix of constants, and then we define the residual sum of squares with respect to this B matrix as the trace of this y minus x B transpose y minus x B matrix. So, this is what the residual sum of squares now would be, and the minimizing B matrix, matrix of constants, which would minimize this RSSB, minimizing this B hat, is given by, it is basically corresponding to a particular column of this Y matrix that we are going to have. This is given by this B matrix as in before. We will have this as X transpose X inverse X transpose this Y matrix. Now, as you can see from this form here, if this matrix Y matrix is consisting of these k columns, and if you consider the ith column of this Y, then this matrix X transpose X inverse X transpose being multiplied with the ith column of this Y matrix is going to give us the ith column of this B hat matrix, right. So, once we have got this B hat matrix, using this B hat, what we can get fit is given by Y hat, which is equal to X times X transpose X inverse X transpose this Y matrix. This basically is that our B hat. So, this is X times B hat. So, this is the fitted value. Now, let us see that if we have really now a k class problem, if a new observation now comes, how we are going to actually look at classifying that particular observation into one of the k possible classes. So, using this setup, under this setup, classification for a new observation x naught is going to be done in the following steps. In the step 1, we compute the fitted value the fitted value of the output. This is with respect to this x naught variable. Now remember, we had a constant term, so let us denote this output, fitted output, by f x naught vector. Now this itself is going to be a vector. This itself is going to be a vector, because if we look at how that is going to be obtained, then this is nothing but 1 is a constant term into this x naught. So that is augmented by this term, that multiplied by this b hat vector, and then we are going to take the transpose of this particular quantity. So this is going to be a k vector. Now if this is a k vector, then corresponding to the ith indicator variable, this is going to give us the ith entry of this k by 1 vector. And hence what we are going to do is to identify the largest component in this f hat vector x naught and classify x to x naught to pi k if we have, say, the kth component of this f hat x naught vector is largest. The logic is simple, because we were looking at y1, y2, yk to be the k indicator variables. The value for which that is going to be equal to 1 in the population was the class membership, and from the sample, if we are going to look at the fitted value corresponding to this x naught, then this is going to be this k vector corresponding to the corresponding fitted values of y1, y2, yk, and then for the component for which we have the largest entry in this particular vector, we are going to classify x naught to pi k if that corresponding entry is going to be the largest. So this section here, the small section here, wherein we just tried to use this 0-1 type of response variable type. So its classification based on 0-1 response regression model. We have seen that how simple that classification rule is based on a simple regression model when we have got a 2 class problem as in this, and we also have a k class problem in general. So we will stop at this particular point in this lecture. In the next lecture, what we are going to look at is nearest neighbor classifiers, and we are also going to look at a logistic discrimination rule. Thank you.